If we track a quantum system through time without looking at it, the mathematics paint a picture of perfect fluid determinism. The state of the system evolves smoothly, never breaking, never jumping. But standard quantum mechanics forces us to accept this smooth evolution is only half the story. The theory relies on two entirely incompatible dynamical laws. The first is that deterministic unitary evolution. As formulated by Erwin Schrödinger, the wave function propagates continuously, guided strictly by energy and time. This diagram illustrates the second law, formulated by John von Neumann and Paul Dirac. When we actually measure the system, that smooth evolution abruptly stops. The wave function collapses instantly to a single random outcome. Hugh Everett proposed a radically elegant solution to this contradiction. Simply drop the collapse postulate entirely. He argued we treat the observer and measuring device as standard physical systems. Notice the interaction here. The vector no longer snaps. Instead, the observer smoothly entangles with the object into a single tensor product. Both outcomes physically occur. By preserving unitary evolution, Everett solved the measurement problem. But in doing so, he destroyed the foundation of quantum probability. If every possible outcome actually happens, asking for the probability of a specific outcome seems mathematically meaningless. This creates a central conflict, because quantum mechanics is ultimately a theory of probability. The Born rule is the specific mathematical tool we use to translate quantum amplitudes into the precise likelihood of an observational outcome, and its influence extends far beyond microscopic lab experiments. As physicist Lev Vaidman points out, the Born rule governs macroscopic physics, even when we do not consciously perceive the randomness. Consider the gradient of colors during a sunset. The entire field of quantum thermodynamics and the scattering of photons in the atmosphere relies strictly on Born rule ratios to dictate what light reaches us. The cone photoreceptors in your eye function as single photon detectors. They process astronomical numbers of quantum events every second, and the ratio of those detections is governed entirely by these probability weights. If the many worlds interpretation is correct, the Born rule cannot merely be a convenient postulate we staple onto the math to make our observations fit. It has to organically emerge from pure unitary Schrödinger dynamics. The most intuitive way physicists try to solve this in a splitting universe is through frequentism. Just count the branches. To see why this fails, we can set up a tangible physical test using historical context. This animation models a Stern-Gerlach experiment. A particle enters a magnetic field in a quantum superposition with vastly unequal amplitudes. The upper path carries an amplitude of square root 1/4, and the lower path carries square root 3/4. Following Everett's deterministic math, the observer at the end of the path entangles with both states. One copy of the observer records up, and an identical copy records down. This bar chart illustrates the mathematical trap of the equal rule. Because there are exactly two observers, standard branch counting dictates that each outcome has an equal 50% probability of existing, blatantly ignoring the amplitude weights. But look at this histogram mapping the actual Born rule predictions. The strict experimental reality is 25% for up and 75% for down. The equal rule contradicts what we actually observe in the laboratory. Naive frequentism is mathematically broken in a many worlds framework. All outcomes may happen, but they do not happen with equal validity. The frequentist approach fails because it makes a fundamental category error. It assumes that worlds can be counted like coins or dice. In reality, Hilbert configuration space is a fluid topology. Decoherence creates approximate, overlapping volumes of probability. There are no sharp boundaries or distinct, discrete universes. The definition of what constitutes a single branch is highly subjective and coarse-grained. You cannot assign an integer value to how many worlds exist. The universal wave function is an uncountably infinite measure space. This makes any derivation based on counting discrete frequencies a mathematical mismatch for the theory's actual geometry. Instead of branch counting, theorists at the Oxford School proposed a different pivot. Perhaps you can derive probability from the behavior of a rational agent. Imagine an agent facing an imminent deterministic split. Before the fission occurs, they must rank their preferences for a quantum game to maximize their expected utility. This decision tree evaluates a preparation, measurement, payment sequence. The agent node branches into multiple payment outcomes based purely on the results of the quantum measurement. As the theorem progresses, the subjective utility variables drop out of the equation. The math isolates the Born rule amplitudes, the absolute square of alpha, as the only rationally sound weighting mechanism for placing a bet. It is an elegant mathematical proof, but it has faced intense skepticism, particularly from Lev Vaidman. Vaidman argues that this decision tree smuggles in unstated physical assumptions. Specifically, the proof covertly relies on the strict prohibition of superluminal signaling. Altering a remote eigenstate cannot change the local probability of an outcome without violating special relativity. That physical constraint is secretly anchoring the decision math. The Deutsch-Wallace theorem identifies how an agent should rationally bet in a splitting universe, but it only works by quietly importing the exact physical constraints it claims to derive from scratch. The final major attempt to solve the probability crisis relies entirely on pure quantum entanglement, a concept Wojciech Zurek calls environment-assisted invariance, or invariance. This diagram outlines his core symmetry argument. The top line represents a physical system, and the bottom line is its entangled environment. A unitary swap of the system states can be perfectly undone by an inverse unitary swap in the environment, realigning the entire configuration. The fatal flaw, marked here at the transformation point, is the assumption that swapping the physical states automatically swaps the probabilities of the outcomes. We do not know the actual mechanism that dictates how a measurement outcome is physically experienced. Assuming perfect probability symmetry under these transformations is really just another way of assuming the Born rule from the start. This leaves theoretical physics in a grand stalemate. Hugh Everett beautifully removed the collapse postulate, but the bill came due in the form of the probability crisis. To preserve the precise statistics that make quantum mechanics function, physicists face a stark ultimatum. You must add explicit, arbitrary physical postulates back into the theory, or you must accept the radical philosophical stance that the objective probabilities governing our universe are nothing more than subjective betting strategies of an agent about to be torn apart by deterministic fission. The many worlds framework provides a mathematically elegant multiverse and continuous evolution, yet it remains frustratingly silent on why we experience this exact sliver of reality.